This lesson deals with Supplemental Problem 16.3. You can find this problem in the ECE202 ebook in the Chapter 16 Supplemental Problems, starting on page 3. Suppose that we have the following monthly rate for a given power plant, where for the first 5,000 kilowatt hours of power consumed, we pay a rate of 4 cents per kilowatt hour. For the next 20,000, 3.5 cents. For the next 75,000, 3 cents. And thing above that, 2.5 cents. Now the total charge for energy is decreased or increased by 0.5% for each 1% that the average power factor is greater than or less than 0.85. Let's calculate the average monthly bill for consuming 180,000 kilowatt hours and 160,000 kilovar hours lagging per month for 16 hours a day. Now let's analyze a proposal to improve the power plant's power factor to 0.85 by adding capacitors at a cost of $10 per kilovar. That is how long it would take for us to break even. Maybe there's a footnote here. This is a homework assignment I gave several years ago, and the rates for your local utility might be quite different. We want to take a look at what the current rates are. All right, our price breaks are at 5,000, 20,000, 75,000, and above that. So for the first 5,000 kilowatt hours, we're going to pay 4 cents. We're going to multiply that by the rate per kilowatt hour, and that's $200. The next rate's for 20,000 kilowatt hours, and we're paying 3.5 cents for that, so it's going to cost $700. And then the next 75,000 kilowatt hours, we're paying 3 cents. Multiply that times this, and I get 2,250. The sum of this is 100,000, so we have 80,000 left over in our consumption, and so we're going to be paying 2.5 cents for that, and that's going to cost $2,000. So if we had a 0.85 power factor, we'd be paying $5,150 per month. Next, we need to figure out what is our power factor, and then how is our rate affected by that. Some of the formulas had days and months. Let's do some conversion. So our first conversion, we convert days per month. And that would be 365 days per 12 months, and that would be an average of 30.417. For 16 hours a day, for 30.417 days, we're looking at 486.67 hours per month. Let's calculate our average power and our reactive power by using the fact that we're consuming 180,000 kilowatt hours per month, and that we're operating 486.7 hours per month. And so the hours cancel, and the months cancel, and we wind up getting 369.86 kilowatts. Likewise, for the reactive power, I've got 160,000 kilovar hours per month with, again, 486.67 hours per month. And those all cancel, and just get the ratio of these two is 328.767 kilovars. Now, we also have our formula from our class notes that the average power is the voltage in RMS times the current in RMS times the cosine of the angle between voltage and current. Likewise, for the reactive power with the sine of theta. So we take the ratio of these two, the voltage and the current drop out. We can flip that over and take Q over P, the ratio of sine to cosine, which is the tangent. We can use that now to calculate the angle. So the arctangent of the reactive power over the real power would be 328.767 K over 369.86 K, and that's an angle then of 41.6 degrees. Power factor then is 0.747. Now we're trying to get up to 0.85, so how much short are we? 0.85 times X would give us 0.747. X would be 0.8788. So let me calculate the percentage that I'm below what I need. It'd be 1 minus 0.8788 times 100%, and that would be 12.12%. For each 1% that we're below 0.85, we're going to have to pay a rate increase of 0.5%. So that's a total then of 6.06%. So our monthly bill then is increased by 1.0606 to be $5,462.09. Let's see if we can lower this bill by getting our power factor up to 0.85. And the angle that we're shooting for then is the inverse cosine of 0.85, which would be 31.788 degrees. This is the angle between voltage and current. Take the tangent of that, and that's going to be our reactive power over our real power, but now the new value of that. And again, we had 369.86 for our average power. So solving then for the new value we need of Q, it's going to be equal to 369.86 K times the tangent of 31.788. And that's 229.22 kilovars. Our old value was 328.767 K. We need to get to 229.22 K. So it's a difference of 99.547 kilovars. It cost us $10 per kilovar to do this. So our total cost is almost $1,000. Okay, what are we going to save per month? Well, this is the rate we would pay if our power factor was 0.85. And we're currently paying this, and so it'd be saving $312 a month. Take the ratio then of the cost here of $995.47 divided by 312.09, and it would take a little bit more than 3 months, about 3.19, to break even. This is actually a pretty good rate for recovering your money. And this is Supplemental Problem 16.3.